Hi, I'm Norman Walpiger. Today we're going to introduce relativistic geometry in the plane. We're going to give a special name to this rather unusual geometry. We're going to call it red geometry. That's to distinguish it from two other geometries that are going to play an important role. The first one is our familiar, ordinary, everyday Euclidean geometry, which we will now call blue geometry. So blue geometry is the geometry that we've been studying so far in this series of videos on rational trigonometry. Today we're going to introduce red geometry, and somewhat later we're going to introduce green geometry, which is another form for essentially the same relativistic geometry. The reason we're going to have three geometries is that it's going to turn out that these three geometries interact in a spectacular way. That's a phenomenon called chromogeometry, and it's going to be a major theme of what happens later on in this series. So, what is red geometry? How does it distinguish itself from blue geometry? Well, both geometries take place in our usual grid plane, with an x-coordinate, a y-coordinate, and as usual. Both geometries share the notions of point, line, and parallel. So there's still a point, there's still a line, these two lines are parallel. These notions are common in both blue and red, and in fact in green geometry too. What's different between them is the notion of perpendicularity. We are going to change the notion of perpendicularity, and that will change everything else too. So let me remind you that the usual notion of perpendicularity, the blue notion, goes like this. Here's a vector 4, 1, over 4, up 1. This direction is perpendicular to this direction. And how do we get this direction? We go over 1 in the opposite direction and up 4. So the vector 4, 1 is blue perpendicular to the vector minus 1, 4. That's our familiar notion of perpendicularity. We're going to abandon that temporarily now and talk about a new notion of perpendicularity. It's very similar algebraically. We're going to say that the vector 4, 1 is red perpendicular to the vector 1, 4. What you get by just interchanging the x and the y coordinates of the vector. So geometrically, what does that mean? Well, here's the vector 4, 1, and here's the vector 1, 4. There's 4, 1, there's 1, 4. In general, a vector AB is perpendicular to vector BA, obtained by reflecting that vector in the line y equals x, the line with slope 1 or slope minus 1. So let's have a look at how this changes our basic setup for rational trigonometry. Well, remember that the main notion of rational trigonometry is the quadrants. Suppose we have a vector AB, and here is the perpendicular vector BA. The way we defined quadrants initially when we started this series was in terms of the area of a square. So we can proceed in a parallel way here. If that's AB and that's BA and these two are perpendicular, we can think of this as being an analog of a square in the red geometry sense. So this is what we'll call a red square. And its area can be described in exactly the same way as in blue geometry. The notion of area is common to both geometries. So what is the area of this little parallelogram? Well, with AB here and BA here, the area is a squared minus b squared. So that motivates our definition of quadrants. The red quadrants between the point x1, y1 and the point x2, y2 is the difference between the x-coordinate squared minus the difference between the y-coordinate squared. Not plus, but rather minus. So we're only changing a sign, but that's going to have many consequences. And I remind you from last video that this is the kind of quadratic form that appears in Einstein's special theory of relativity. In two space-time dimensions, we were talking about x squared minus t squared. That's exactly this kind of geometry that we're talking about here. As an example, here is the red quadrants between the point 0, 0 and 4, 1. We take the difference between the x-coordinates squared, that's 16. The difference between the y-coordinates squared, that's 1. We get 15. How about the quadrants between 0, 0 and 2, 8? Difference in x-coordinates squared, it's 2 squared. Difference in y-coordinates squared, 8 squared. We have to take the difference, so it's 4 minus 64, that's minus 60. We can get a negative quadrants this way. And the quadrants between 4, 1 and 2, 8, well, we take the difference here, that's 2 minus 4, that's minus 2, all squared. The difference here, 8 and 1, that's 7, 7 squared, so we have 4 minus 49, that's minus 45. Now these points here have been chosen so that the vector 4, 1 is perpendicular to the vector 2, 8. That's just a multiple of 1, 4. So this is actually a right triangle here in a perpendicular sense of red geometry. And lo and behold, we see that this quadrants plus this quadrants equals this quadrants, suggesting that Pythagoras' theorem is also going to be holding in this red geometry, even though the quadrants have a completely different interpretation as before. Well, now that we have a red quadrants, what about a red spread between two lines? So here are two lines, L1 and L2, and these lines are exactly the same lines as the ones we've been talking about before. How are we going to define the spread between them in the red geometry? Here is the definition that we're going to use. The red spread between these two lines is minus a1b2 minus a2b1 squared divided by a1 squared minus b1 squared times a2 squared minus b2 squared. The difference between the blue geometry is that there's a minus sign here instead of a plus sign. There's a minus sign here instead of a plus sign. This is exactly the same as before. And there's an additional minus sign in front. So there are 3 new minus signs. Something happens with this definition that doesn't happen with blue geometry. It's perfectly possible for one of these factors, or both of them, to be 0. If a1 squared minus b1 squared equals 0, then L1 is called a null line. That, of course, just amounts to the condition that a1 and b1 are either equal or negatives of each other. This is a new definition, the idea of a null line. And it's very much in the spirit of Einstein's special theory of relativity, where null lines are the world lines of light, photons. Alright, so for this spread between L1 and L2 to make sense, this red spread, we require that both L1 and L2 be non-null lines. In other words, we insist that these denominators are not 0, of course. Alright, so an example. Here's a line L1 with equation x minus 2y plus 3 equals 0. So it's going to be given by the proportion 1 to minus 2 to 3. And another line with equation 4x minus 3y plus 7 equals 0. So it's given by the proportion 4 to minus 3 to 7. Now the 3 and the 7 have nothing to do with the spread. It's only the first two coefficients that matter. So the spread between them, the red spread, I should have put an R here, is minus 1 times minus 3 minus 4 times minus 2, all squared. That's the numerator. And under here, 1 squared minus 2 squared, that's one factor, and 4 squared minus 3 squared, that's another factor. So minus 3 plus 8, that's 5, so we have 5 squared. There's a minus sign here that we'll bring there. This is minus 3, 16 minus 9 is 7. So we get minus 25 over minus 21, or 25 over 21. The red spread between these two lines. And note that this spread is a number bigger than 1, which is something that can never happen with blue geometry. With our ordinary regular rational trigonometry, the spread is always between 0 and 1. So there's obviously a lot of new things going to be happening here with this geometry. And next time we're going to have a look at a lot of different examples to give you some intuition as to how this geometry goes. We're aiming towards what are the main laws of trigonometry in this setting. So I hope you'll join me for that. I'm Norman Wallberger. Thanks for listening.